Right. In this tutorial or lesson, I'll be discussing deadlocks. I am following closely the textbook by Silvershats, and I'll be going through a lot of the issues they highlight in the deadlock chapter. Before treating deadlocks, I will assume you have some knowledge about how threads work, how processes work, how to use locks. It helps to understand what's going on. But even if you don't, at least you can ignore the code and learn the principles. The principles and concepts about deadlocks are relevant, and you don't need to be a developer, programmer, engineer. Even if you are a normal person, when I say normal, I don't mean that computer scientists are normal. Even if you're a non-computer science person, you should be able to appreciate some of the things that I highlight. So the mindset, as I said, is important. It's important, I think, for you to, I said the word think. That means you listen, you should read, you should explore, you should try. And whenever we say something, don't just memorize. I would say sit and think. When I say thinking, it means you can try and come up with some ideas on your own, try and come up with some examples, counterexamples, comparisons, and so on. Okay, so let's begin. There are many things we'll go through for deadlocks, but let's go through some of the main ideas. So for deadlocks to occur, and deadlock is, I think we're just using the English definition of what a deadlock means. Now, according to the dictionary, this is Merriam-Webster, you can go online, check it out. The definition of a deadlock is a situation in which an agreement cannot be made, a situation in which any disagreement is impossible, and neither side will give up something that it wants. A situation in which players, teams, etc. have the same score. So this means if someone says there's a deadlock in a computer science sense, programs that are running, it means they are locked up and someone is waiting for something but doesn't want to give up something that it has. The same way occurs in nature or in society, right? So let's go back to the slides and take a look at what we have in computer science. Right. So from the definition, we can tell that there will be, or there have to be, several processes. When I say processes, please don't say, oh, I'm dealing with threads, so there can't be deadlocks. Think. Anything we're teaching here, just expand, think about it. It's not just about processes, it's about more than processes. It can be about societies, it can be about ecosystems, it could be about anything. So anytime we teach something, if you're finding computer science difficult and boring, sometimes you just have to sit down, relax, take a deep breath and think, come up with some examples. Right? So don't just think, oh, this is about software, this always has to be about some code. No. And as I keep saying, I believe computer scientists would actually make great leaders, managers, entrepreneurs, everything. They really should be able to do everything and anything because the training is really complete. So let's continue, right? So several processes and a finite number of resources. So when there is a limited number of stuff, of anything, and there are multiple people or items or competing for it, that means deadlocks can occur. And usually, when people want to use requests, or when processes want to use request, they would request it, use it, and when they finish, they'll release it. Now, some issues that we talked about before is we would be using some type of locking mechanism to try and avoid race conditions. So in previous sections, we talked about race conditions. So if you don't know what that is, please look it up. But even though we prevent race conditions by using things like mutex, deadlocks are still possible. So this is an example that I'll be using to try and encourage you, or to try and help you understand what will be happening with deadlocks. So in this case, transferring money from one account to another. In order to transfer money from one account to another, you first have to lock the first account, in this case account A, lock the second account, account B, do your various transactions or operations on it, and when you finish, you release the accounts you are holding. This makes sure, once you can hold both accounts, it makes sure that nobody can mess up while you are working with the accounts. Right, so I am expanding this. So instead of having one process, so remember I said if deadlocks are going to occur, you usually need multiple resources, in this case account A and account B, and multiple processes. If there is just one process in a system, there won't be deadlocks. If there are no resources in a system, or there's only one resource, I don't expect there to be a deadlock. Right, so let's look at this case. Now, as you can see from this, a deadlock can occur if we put in these various transitions. So for example, I'm using, this is standard graph notation that the textbook will be using as well. Most people use this. If you decide to use a different notation, simply remember to be consistent. Now look at the notation carefully. This means that account A is currently in possession of banker 1. That means the arrow is going from the resource to the process. And similarly, account B is held by banker number 2. Banker number 2, arrow going from him to resource A, means he's requesting resource or account A, and banker number 1 is requesting account B. They are all using the same code, but they, let's say account A and B started at the same time, and they are all asking for their first account, second account, and one person is wanting to move from A to B, one person from B to A. That means that they are grabbing the first account, that is the source account. So banker A grabs account A and banker 2 grabs account B. They realize now they are stuck because nobody wants to give up and nobody can continue, and this is the classical deadlock. In your textbook, your diagrams may be black and white, so just look at the direction of the arrows. Now, as far as format, another way to represent this information is to use nodes and edges. In the text, they tend to list these as sets. So that means your processes are banker 1, banker 2. In the textbook, they may write P1, P2, P3, P4, and so on, without losing any concepts. Generalizing, you should be able to apply this. So if you read a text and you see variables with subscripts, don't get alarmed. It's the same thing. Similarly, the resources are listed account A, account B, and those are just listing the other type of node. So these are nodes, there are 4 nodes, that's what's being listed. E means edges. If the textbook doesn't make that clear, that's what it means. And an edge usually is traced from a source to a destination. So we have one account A to banker 1, and that's represented by this line. Account B to banker 2, that's represented by this line. Banker 2 to account A, that's represented by that line. And of course, banker 1 to account B. So you should be able to, given a diagram, come up with the notation representing it in text form, or going from plain text, being given the different nodes and the edges, should be able to represent it in diagram form. Right. So these are the conditions that are necessary for a deadlock. Of course, as I said, we assume already that there are multiple resources and multiple processes. But usually in that chapter, when they say the conditions, they are listed out as mutual exclusivity, holding and waiting, no preemption, and circular waiting. Right. A mutual exclusivity means that when you hold a resource, only one person is holding a resource, or a limited number of people is holding a resource. The book says, well, I hope you understand, just mutual exclusivity. Even though it doesn't, I think people would assume that if you have a binary lock or 0-1 lock, that means that that's the only time deadlocks can occur. Deadlocks can occur if you have semaphores. Remember, semaphores were like locks, except that they had multiple, they had a capacity. A semaphore could have a capacity of 10, meaning about 10 people could be waiting on a semaphore, or potentially in hold of a ticket or a lock from a semaphore. Right. Hold and wait means that a process would hold something and be waiting for something else. No preemption means when a process is holding onto a resource, it doesn't let it go. And circular wait means you will be able to find a circle within the diagram. So let's take a look at this. So you can see from this one, So let's look at the conditions. Mutual exclusivity. You can see from here that every account can be held by at most one person. So account A is held by banker 1, and that's it. You can't have account A being held by 2 bankers at the same time. So that's mutual exclusivity. Just stated that here. We also talked about hold and wait. Look at it carefully. You can see banker A1 is holding on to account A and is waiting for account B. Similarly, banker 2 is holding on to account B and is waiting for account A. No preemption means, of course, account A is held by banker 1 and he doesn't want to let it go. She doesn't want to let it go. And hold and wait along with no preemption would mean that no one is allowed to maybe tell banker 1, hey, let go and let the other banker finish a transaction. So those are the 4 conditions, necessary conditions for deadlock. Right, so if you're able to break any of these, deadlocks won't occur. We'll go through all of them. Now, in this chapter, we will go through at least some techniques or some ways that we deal with deadlocks. And the first one, they're in groups. The first group is has to do with prevention. The second group has to do with avoidance. The difference between prevention and avoidance you would see when we go through the different algorithms or techniques used for dealing with deadlocks. Detection, that means trying to figure out if a deadlock has occurred, and recovery, of course, means when a deadlock has occurred, how do you maybe undo or recover from it? I mean, these are just English. So the difficulty, of course, in this section or this chapter is understanding the different algorithms. But I don't think the algorithms are maybe understandable just by computer scientists. I am sure that if you show these algorithms to someone in secondary school or primary school and step them through it, they should be able to understand. I've done that before. I don't think the topics we are treating here are so abstract. They are very relatable. So please take your time, step through, make sure you follow the steps of any algorithm or the logic, and you should be fine. Right. And of course, when we finish doing all of this, we'll talk about a few other issues. So let's go through it, starting with prevention. Now, if we are going to prevent deadlocks, and the main thing, as I said, prevention is treated differently. When we say prevention, it's different from avoidance. And most of the prevention techniques go along with the 4 conditions that we listed. So the 4 conditions that we listed directly with them. First one is mutual exclusivity. Now, sometimes, in order to eliminate mutual exclusivity, what you could do, so I should have said eliminate mutual exclusivity, eliminate hold and wait, eliminate no preemption, eliminate circular waiting. So when we want to eliminate mutual exclusivity, what it means is we have to try and find a way so that mutual exclusivity doesn't hold. Now, in some systems, what they would do is they would try and figure out, is it possible to have both reader and writer locks? So sometimes you don't have to just use mutexes. You can try and find out, can I use read-write locks? Because if you have read-write locks, it will be possible to have multiple readers holding a resource. And what that would mean is they will not be interfering with each other, and there can be some sort of progress, even though the resources are held by multiple people. But because you are sharing, so that's why I said readers, then it will be possible for you to eliminate mutual exclusivity. It doesn't mean you can always eliminate mutual exclusivity, because it's not everything that you can say, let's share. For example, if you have a printer, like it or not, the printer has to finish printing the first page of a document before moving to the second page of a document. It cannot be printing document 1 at the same time as printing document 2, the same or different pages at the same time. You can imagine the mess it would be. It would almost be like trying to put multiple windows into one place and making them transparent so that the bits are overwriting each other. I don't think it will work out, right? So mutual exclusivity is the first. The second is holding and waiting. Now, if we don't want processes to hold and wait, it means we must have some protocols in place. And in the textbook, they would say protocol. So protocol usually sequence of steps, some algorithm, some plan for solving some problem or getting something done, right? So hold and wait, we can say before any process starts, it has to request all the resources it needs. If it has requested all the resources it needs before it starts, that means it could never lock. It would never be in a hold and wait scenario because it has all the resources. So why would it be waiting for something else? Similarly, we could also say if a process is going to be requesting for resources, it has to let go of what it already has. Because there are some cases where a program is running or a process is going on and it doesn't know all the resources it would ever need. In that case, it would say, well, I can see at this point I need resource 1, and it will keep going, and later discovers needs 2, 3, 4, and so on. That means anytime it discovers it needs more, it would keep track of the things that it currently has, figure out what it needs, and let go of everything and try and acquire them all in one go so that it wouldn't have to ever wait. Right. There's also no preemption. In that case, what we usually do is anytime a process is requesting for a resource and it has to wait, then the process automatically yields all the resources it has. So that means you don't have, so this is more like processes being nice to themselves. So say, well, I don't want to stop you, so just let go of everything. Right. And the other one too is, of course, this one we are saying no preemption. To break it, we will be preempting. So yes, let go of your resources. And the other one is if you are waiting for something, so long as you are not currently running and you're waiting for a resource, if someone wants a resource and the person is running, they can take it from you, right? So this is almost like saying there's someone in a banking hall and the person is currently at the head of the queue speaking to the banker, and this person wants to sign a check. That means he's the person at the window. He's the first person. That means that if you're the last person that just walked into the bank and grabbed the pen, please give the pen to the guy at the desk so he can sign his check, take his money and go home. That's the idea. Right. And of course we have preventing circular waits. That means we have to, this is a very interesting one. We assign numbers to the resources and insist that when you are requesting for items, you follow and ask in the order in which the resources are assigned the numbers. So let's take a look at how we would apply this to the case we had before. Right. So in this account, so I'll be going between this slide and that slide a lot in the explanation. So the first one is mutual exclusion, sharing. Is sharing possible here? I don't think so. In some cases, yes. Maybe you have a program, you're just playing music, something else is displaying a presentation. Yes, you can share. Good. But sometimes you can't. In this case, I don't think you can say they should share their account. So we won't hold in this case. Hold and wait. So we said two things. You can either request all your resources before starting, or make sure when you're asking for things, don't be holding on to other things. So look at this. Banker 1 would like to use account 1 and account B. If Banker 1 is starting, we can say, well, don't just ask for one thing and later ask for the other. Why don't you ask for the two things you need, account A and account B, so nobody will ever preempt you, or you won't hold something and wait. So that is one case. The second case we said was if you have an item, for example, Banker 1 is holding account A, and you realize you need more things, such as account B, Banker 1 should let go of account A before asking again for the two items. So you may wonder, why is this so? And the reason why this works is, or why this would be working is, anytime you are asking for more things, we assume that you weren't able to finish with what you had. So that means let go of everything you had. And if you let go, so for example, maybe Banker 2 was waiting. If you let go of A, if Banker 1 had account A and he let go of that one, if someone else were waiting for it, that person could take the two items and finish their work. Now we assume often that processes in this scenario, once they have all the resources they need, they will run and eventually stop. So letting go would allow someone else to acquire other resources they need, so they stop. Now we have this one called implicit yield on unsatisfied request. Same thing, meaning that if Banker 1 already had account A and was asking for account B, it would have to let go of the account is already holding on to. And of course, the other one that we said was, it's a little bit interesting, but the same twist, meaning that if banker 1 were waiting for account A and was in a waiting state, and banker 2 was currently running, holding on to B, banker 2 would be allowed to take account 1 from banker 1. That means banker 1 will be told, hey, please let go, and he will have to start his transaction from scratch. Now, the last thing is circular waiting. Right. Now, if you look at this one, if, for example, we said every time you're going to ask for something, ask for it in alphabetical order. So banker 1, you hold on to account A because that's the first item, and then you ask for account B. That means that banker 2, who needs the 2 items as well, has to first of all ask for account A. And because banker 1 has account A, banker 2 will not take account B because account A is already with banker 1. So it forces an ordering. I know I've gone through this very quickly. You can reverse, take your time, play it again, and try and understand. Or try and put it in your own words to make sense. Right. So those are the various scenarios. Now, if you look at this carefully, please note that it's a circle. It looks like, so look at this. From here, I go to here. From here, banker 1, I go to account B. From account B, I go to banker 2. Banker 2, I go to A. There is a circle here. If you see any diagram, and you can go from one point, starting location, go through different nodes and come to the other point, you have made a loop or a circle of some form. That means a deadlock has occurred. Right, so that is prevention. Let's go on to avoidance. Avoidance means trying to sort of manage the information so you don't end up in deadlock scenario. This is usually done by some algorithms or paying attention to the state of the system. Right. So the first thing we say is we can try and keep track of our safe state. Now, a safe state means that you are in a scenario such that you know there can be a sequence of acquisitions and releases, or so that you can complete your work. Right. So that is what safe state and safe sequences are about. The second one, of course, is resource allocation graphs. And that looks like the circles when we're looking for the circular diagram. So here we're trying to find circles. The resource allocation graph tries to find these circles, or at least tries to say, can I detect when they will happen? The banker's algorithm is a different type of approach where you're trying to keep track of multiple resources. Now, I'm just going to review because there was a car passing by with a lot of noise. Okay, so safe state, as I said, you try and keep track of, is it possible for me to give a sequence of acquisitions and releases so I can make sure every process finishes. Resource allocation graph, that means that we look at the graph that we were drawing before and try and determine, even before the processes start, to try and know what they are likely to request for. And so if we ever detect any type of loop, we prevent it from happening. The banker's algorithm, that means we need to keep track of what people need, that's the maximum, the number of items we've allocated to everybody, the number of items people need. And remember, if someone needs a maximum number of certain type of resource and has been allocated a certain quantity, the needed amount is simply maximum minus allocated. And we also keep track of all the available resources. Right. So let's take a look at some of these. So safe state. Looking at safe states and safe sequences. If you look at the diagram we had before where there was a deadlock, one of the things that a system can do before it allows operations to happen is to try and think through, is it possible to have a sequence of acquisitions such that deadlocks won't occur? So starting from the initial state where banker 1, banker 2 are there, it is possible to have a set of safe sequences. So for example, account A can go to banker 1, account B goes to banker 2, banker 1 uses them, releases A and B, and then banker 2 takes care of, takes account A, takes account B, and then releases them. That is the safe sequence. This is not difficult to do. You may have to sit down and think through it a bit in an exam scenario, But if you have software, a lot of people have tools that can automatically do this, because it's just a matter of going through the different options to see, is it possible to complete successfully. So that's what we mean by safe state. So we would say that we are in a safe state, for example, here, because we know that it is possible for me to find some safe sequence and manage to get everybody to complete. Now, for example, if I was only missing, if account A was held by banker 1 and account B was held by banker 2, and even though I hadn't made these requests, I am in an unsafe state, because there is no way for me to give requests, no matter how I do it. Should I give this one first or that one first, so I can complete successfully? That's the difference between safe and unsafe states. Now, the other one we talked about was before any of the transactions begin. So let me just go back to this, the resource allocation graph. So before the transactions begin, we can take a look at it and say, hey, what are all the possible requests for resources that can be made? And we use claim edges. These are dashed lines between the nodes instead of thick lines. And that means anytime a request is made, we make a solid line. And if during the request we detect that a loop is possible, because remember, if we know what you'll be requesting for in future, we can try and detect if a loop will be possible based on your request. Then we can prevent deadlocks from occurring. Look at the text to get more on this. All right. The other one is the banker's algorithm. And what the banker's algorithm, so it's almost like you're a banker. You have a set of resources and you want to manage those resources. You would like it to be that nobody can hold on to all the resources such that there's a deadlock scenario, or the resources are distributed. So usually you keep track of all the resources available, what is allocated, and what do people need. So let me just do a short example with this. Right. So I'm going to start off and say I have a system that has 10 items. 10 of item A, 10 of item B, 10 of item C. For the people who are saying, oh, this is abstract, please just think of any scenario. Maybe the example I tend to use a lot is, suppose you had maybe different types of laborers, laborer type A, or different types of workers. Maybe you had accountants, you had computer scientists, and you had what's the last group? Maybe artists, graphic artists, and they needed to work on a project, and that means they needed to work together on a project. And different companies would be coming to ask for these guys to work on projects for them. So I will be looking at the banker's algorithm. I've filled in some values for the banker. So the banker starts off with, and as I said, I write A, B, C as resource names, but these could maybe be trucks, wheelbarrows, shovels. It just means there are 10 of some resource, 10 of another resource, and 10 of a third resource. Or maybe you don't like 10, let's use 8. Maybe that'll make you happier. 8, and they don't have to be the same amount. We can say they are 8, 9, and 10. Right. And so what the banker does, and just think about it, what a banker does is anytime someone asks for something. So for example, if process A goes to the bank and says, I would like to be given, and remember, he needs 6, if he's able to have his hand on 6 of A's, 6 B's, and 4 C's, he'll finish his work. So if he goes and says, I would like to have 6 A's, please, that means that I have now taken 6 out of the total of 8 items. That means I only have 2 to give. And someone else can say, hey, I know I'm going to need 4, but why don't you give me 2 of these? And remember, the idea with the banker's algorithm is you can't put the bank into red. Yeah, in computer science, you shouldn't be putting banks into red. It would be very interesting if a computer scientist actually run a bank according to computer science principles. I think it would be really interesting and really incredibly awesome. So we understand these things. Of course, real banks operate in totally different ways, but this is a logically correct bank, let's put it that way, where we don't have phantom money or digital things that don't exist. Everything is there. So even though he needs 4 items, I mean, he's acquired 2 of them and needs 2 more, right? And he comes and says, but at this point, if processes, once they hold on to things, so for example, one guy came in and picked up 6 of one item. Right now we are in an unsafe state. Remember when we said unsafe? It means there's no way that people can acquire resources and finish. Oh well, I think there is a way in this case, but let's say there is a way to acquire resources and finish, because in this state where it's 6-0, in order for this to finish, that means that I could decide to give B 6 of these B's, right, as well as it needs 4 of these C's. That means process 1 has been able to acquire everything, and that means since it's acquired everything, it will run for a while and let go of everything, right? Because remember, they won't run forever. So 0, 0, 0, you can let it go so that someone else can also have a go, right? Now let's look at a different scenario. Well, that means that process A would then be done, and then this guy can also be given all that he needs. That means he can then take he needs 4 of these and 6 of those. Once he has all of them, runs for a while and then gets done, and then this guy can be given his resources as well, 1, 7, and 4. You run for a while and then he'll also be done. So in this case, there is a way to run these and have them stop. Right. Now we were in a scenario earlier where we had 6 and 2 assigned that way. Now for example, what's going to happen if process B also came along and said, well, I need 7 of these? Right now, let's see, are we in an unsafe state, meaning there is no way to end gracefully? I think we are, because if process 2 has 7 of the B's, there are only 2 of them left. Process A can never finish because someone has it, so process A is stuck. And at the same time, process B will try and say, well, I needed 10 of the C's, or he needed 6 C's, so goes ahead to acquire them. But it's never able to get more A's. It needs a total of 4 A's to finish, and that means it's stuck. And this is more or less the banker's algorithm. It works the same way as when we had safe and unsafe states, when we had one item. But with the banker's algorithm, the idea is there's multiple. There are many of the same item, different types of resources. So you can think of a bank maybe having, maybe A represents dollars, B represents pounds, C represents CDs, and they're trying to figure out how do we get our money to our customers so they can finish the transactions, bring the money back, and we can loan it back again to someone else. And this is the banker's algorithm. So in the banker's algorithm, when someone says, can you tell if this is a safe state? It means I have to look through and be able to say, I can prove that given the data we have, I can find a way out for you. Or in this case, you can't find a way out. And the reason you can't find a way out is process 2 has all of the B's, meaning process 1 is stuck. And of course, if process 1 is stuck, that means process 3 will never get any more A's for it to finish because it needed 4 of the A's. This is the banker's algorithm. You can play with this. Let me give you a different setup and you can tell me if it's possible. So for example, if I have this, am I in a safe state? So I'm going to put some numbers in here and show you how the banker's algorithm would work. Now the other ways when we're detecting deadlocks is to look at wait for graphs. So we look at the system we have and we ask ourselves, are there people waiting for other items? And we do this by constructing a wait for graph. It comes from the resource allocation graph. So let's take a look at that. So this is a diagram and it's showing, this is the one we started with, that banker 1 was using account A and banker 2 was requesting account A. That means that there is a waiting relationship between banker 1 and banker 2. Other words, banker 2 is waiting for banker 1. Similarly, since banker 1 wants account B and banker 2 has it, that means the banker 1 is waiting for account 2. In the wait for graph, we will be eliminating the resource nodes, but simply replacing them with edges showing which process is waiting for which other. So let's look at this. On the left hand side, that's here, I'm showing the processes, those are in circles, and the resources So this resource goes here, resource, and I picked one of them. So I picked process 3 and 2 and looked at the sharing. So you can see process 3 wants this resource and process 2 has it. That means that we have a wait for edge here, and we can remove this node and just replace that whole transition or that whole sequence with this item. So this is what's going to happen eventually. And so if you look at it carefully, that means, for example, I have P1 is wanting something from P3. P5 wants something from P3. And you can see the diagram there. P3 wants something from P2. That's there. P4, here you can see, wants something from P6. All the other things are eliminated. You see the diagram becomes much simpler, and you can tell who is waiting for what. If after you eliminate all these resources, you realize that there is no circular loop, that means that there is no deadlock. Now please note the resources that are not used, like this one, are totally removed in the wait for graph, and the resources that are held by just one person, like P1 has this one, it's not in use in the wait for graph because no one is waiting for it. But those ones, such as this one, just above P2, P3 is waiting for it, and so that means we replace that with an edge. And so we use this sort of analysis, a wait for graph. Now, when we talk about deadlock recovery, it means that something's gone wrong and we would like to undo what we did. Right. And usually we would abort the processes. So if you've been using computers, sometimes things freeze, and what people do is they start shutting down things. It's the same idea. Even those who are not computer scientists do this because they know that the computer is freezing because maybe it's overwhelmed, or they haven't thought about it, but sometimes there's a deadlock going on. And by killing all the deadlock processes, so if you went to your task manager, you look at all those processes that are just waiting or frozen, or which windows are frozen, you start closing them. Right, so that's what can be done. Or instead of trying to kill all of them at once, you can pick a few, make some guesses, and kill a process one at a time until the deadlock is resolved. And so the issue there is, when should you detect deadlocks? And of course, how do you choose your victims for deadlocks? Now, there are other issues that exist. Right, so the other issues that exist when resolving deadlocks, remember, usually you're trying to figure out which process do you kill. And so there are many issues that are discussed. The ones I put into brackets extra means these are ones I've encountered in projects. So for example, when you're trying to kill a process, trying to figure out, you can try and ask, what's the priority? So if you have high priority processes and low priority processes, you could decide you'll kill off the low priority processes. Other times you could look at which resources are being used. If a process is using a lot of resources, it will be a pain to have to restart it because maybe it was very difficult for it to get all the resources it had. So you'd say, well, why don't you finish and then let go? As opposed to saying, this process that had so many resources has to be restarted. That means it's going to come back and be asking for a lot of resources. And sometimes you could also ask yourself the flip case, how many more resources does someone need? Because sometimes you look at it and say, well, this process needs just one resource to finish. And if that can have that resource, you can give it to it, and that's one less process to deal with. You can look at the time you spent, because maybe if a process has been running for a long time, maybe a day, it's painful to say, well, let's restart this process, when most of the other processes have been running for a minute or an hour or so. Sometimes you want to say, maybe the processes that have been running for a long time should get higher priority. Other times you could look at, is the process interactive, or is this just something running in the background? For the interactive processes, sometimes someone is on the other end looking at a screen expecting some feedback. So if you killed it, maybe you'll not be able to get back to where you were. So sometimes you ask yourself, should I kill this or not? So the type of process matters, as does the type of resource, because sometimes the resource you have, if you preempted it, you would destroy things. For example, if you have a hard drive and someone is doing backup and they are halfway through, you don't want to preempt them. You want to let them finish the backup so the hard drive can be automatically ejected and something else can happen. Right? So those are some of the issues when we talk about the cost. So this is, remember, when you're trying to recover, we would have to kill processes sometimes. And if we're going to be killing process, as I said, we might have to discuss the cost. What's the cost of this? The other thing is, when you kill processes or take resources from people, you have to worry about rolling back. Rolling back means undoing what has been done. So if it's about an account that was being used by a banker and the banker was told to undo his work, how easy is it for him to undo his work? If he can undo his work and restore the earlier values, that's great. Now, while all this is going on, we also worry about starvation. Starvation meaning that sometimes, because you keep killing a process over and over, maybe he grabs a few resources, he waits for somebody, you kill him. He grabs a few resources, you kill him. You can end up in a starvation scenario. Starvation, remember, was when a process is unable to make any progress because it never ends. It just keeps. So it means it may be running, but it never gets to finish. So it gets restarted and gets restarted. So imagine, for example, your computer is trying to do an update, or you're trying to download a file. You download to 99%, someone stops you, says start again. You download to 50%, start again. That's a starvation scenario, right? So those are the issues with deadlocks as far as, in this case, recovery. Now, I'm going to look at a few examples with code to show you how deadlocks occur or can occur, right? So let's take a look at the banker scenario, right? So remember, we had a bank, and this is a banker. The constructor takes two accounts, account A and account B, and an amount. And what the banker does when it runs is to say, let me take some amount of money from account A and put it into account B, and it saves the balance. And then when I have debug on, so there's a static variable I defined. When it's on, I just print a message. I just want to show you how it works. The account is a simple class that has a balance variable. Now what I do is, for debug mode, I just use 10 items, or 10 bankers in this case, so that I can print and show you what's going on. But for larger numbers such as 10,000, it doesn't make sense for me to try and print everything because it's going to be very slow. I want to complete this resource or this tutorial for you. So let's go through all that's happening. So I'm doing a modulo here, meaning that I'm saying that all the, so this is 0, modulo 0. So all the even numbered bankers are going to be transferring money from account A to account B. But all the odd numbered bankers are transferring money from account B to account A. And what I'm doing is I put a fixed amount of money into account A and a fixed amount of money into account B. Now, if the total number of bankers is an even number, this is mathematics, and I'm moving from one to the other, or from the other, from A to B or B to A, that means, for example, banker 0 move from A to B, banker 1 will move from B to A, banker 2 will move from A to B, and so on. So if I can keep this going, then it means that at the end of this program, I expect that the total number of transactions one way should be the same as the total number of transactions the other way. So let me show you how this would work. So let's run this and see what's going to happen. When we run it, we see account A contains 1,000. What I do is I multiply the number of bankers by how much each person will be moving each time. And account B contains 1,000. Account A plus B is 2,000. And we start off. So this is what I was saying. Banker 0 moves from A to B. Let me just check this. I think there is a printing. Just see how I'm printing. Okay, so that was it. I have to. It should be B. This should be B. So you can see what's going on. So let's run this. So you can see 1,000 becomes 900 and 1,000 becomes 1,100. And for B, 1,100 goes back to 1,000 and 900 becomes 1,000. So that means every banker, so all the odd numbered bankers are doing the same operation. They're moving 100 from one account to the other. And all the even numbered bankers are doing the same. When running serial, so serial means I am running one after the other after the other. So let's look through my main. In my main, I simply call the run method, right, in the loop. And the run method, sorry, just jumped to the wrong place. Right, what the run method does, so this is my run method. the run method is simply moving the money based on the transaction. So even if I had 10,000 items, so for example, if I say I'm not debugging anymore, false, I want to run with a full speed, so this is 10,000 bankers, and I run this, I am now going to have, at the end of the day, 2 million was the end amount, and previously was also 2 million. Now let's take a look at transferring. A poor case of transferring. What I've been doing is anytime I do example code, I show you one example where there are errors. So in this case, this is the second example. Starting again, the transaction is there, but in the run method, I am not using any locks, but I am still going to be using threads. So you can see I have, if debug, I do some things, and what I'm going to try and do is to print the information using the variables. So this is A and B. Right, now I'm going to go through, we're going to look at the main. So I can see here I have 10 items, 10 banks if I'm doing debugging. Let's run it and see what happens. Right, so okay, so this is when I'm not doing debugging and I'm running everything. You can see that I actually end up, initially I had 2 million in units, but at the end, if I'm not using any type of synchronization, no locks, I end up having the wrong value. So let's run this again so you can see what's going on. Run it again. So I think the threads are running. Run. Wow. So I get different values. It's close, but it's different values. I run it again. The threads are running. So I keep getting different values. Now, when I am debugging, so when I turn debugging on, I use fewer number of bankers, so you can see the messages that are being printed. So when I run this, you can see it says banker A was using this, was using that. Even though it's printing that it's locked, it didn't actually lock it. Remember I said for this specific case I am not doing any locking, but I'm still going to try and do threads. So you can see each person is saying what they're doing, and if you go through carefully, so here's a good interesting example. One banker moved an amount. Let me just try and find an example. Okay, so this one is so small that it doesn't really matter. Remember, for small numbers, sometimes you will not see the error show up. But when the number of bankers grows, so in this case, when I moved to 10,000, then I started to see cases where the amounts were not adding up. So these are, the bankers are moving money from one to the other, and again, they don't add up. It's by a small amount, but if you're a computer scientist, you care about little details, right? So let's look at the deadlock scenario. Remember with the deadlock scenario, so let's pull up our presentation and look at the deadlock. Just scrolling all the way to the beginning. This was a deadlock scenario. Banker 1 was holding this account, this banker has this account, and each one is also waiting, so that's a deadlock. Let's look at how we can have that happen in our code. Alright, so we are going to be looking at using locks, and even though we are using locks, I'm going to show a scenario in which deadlock occurs. Now if you look at our code, we have in our run, this is someone saying synchronize on account A and then synchronize on account B. But if you look at this, it means for somebody, for example, moving from A to B, this one will say synchronize on A, and this one will say synchronize on what I think is my first account. But if I am seeing my first account as account A and he's seeing his first account as account B, that means that one thread is holding A, one thread is holding B. And the reason why this is occurring, we'll move down into our where we set up the initialization of the constructor. So if you scroll up a bit and you look at your constructor, it says account A, account B. It means I'm passing two account variables, and so whichever one I pass first will be locked, and the second, in this case, the second item would then be locked. And if you look at this, that's exactly what it's doing. It says lock up my first account, lock up my second account. And if I scroll down a bit, this is where I have my main, and in my main, if you keep scrolling, you'd find where I create the bankers. For the even bankers, the first account is A. For the odd bankers is B. And for the even, the second account is B. Whilst for the odd, the second account is A. So it means these guys are going to lock up this one first. Meanwhile, the B's are locking that one. So in order to show you how the deadlock will occur, I'll run this first with debug mode on. That's the banker. That's the debug. It's on. And that means it will be using 10 items or 10 bankers to run this. So let's run it. Okay, a deadlock has occurred even though they're just 10 items. So just going to resize, trying to resize my window here. So it says running, right, running, and you can see here it says banker 0 went ahead, banker 1, banker 2, but no, it gets to a point. Look at this, it says banker 7. Actually, that means you don't have control of when threads start. I created a bunch of threads and they're just running, didn't have any control. So thread 7 actually got a jump on thread 6, and thread 7 had locked up account B and thread 6 had locked up account A. Then it stopped. Now, one of the reasons why deadlocks are dangerous is sometimes if you have bad code, it will happen, and sometimes it won't happen. So it's possible to write code you keep testing in your test facility with all the software, and you will not detect the error. Let me run this again. So I stopped it. Let me run it again. It's even stopped earlier, 5 and 6. Now, there will be some cases. So sometimes you have a scenario where this is just getting worse and worse, right? Like in this case, right off the bat, it froze. Try again. This time it went a little bit further. So it means that these are sort of non-deterministic runs. We can't tell when a deadlock will occur, because whenever we run it, depending on how lucky we get, it may freeze up, right? So it means we are running into a scenario where one is grabbing the other and the other is grabbing another, and we are running into a deadlock scenario. Now, if you're doing a test and you want to see if this is really happening, one of the things I do, this is not something I would say everybody should do, but one of the things you can do is you can sometimes during testing do thread.sleep. You just need to sleep for a very short period of time, and what that happens is you are letting go of the processor. I believe there are other methods available. There's also yield. So you can say, I want to give up my my share of the CPU immediately and let someone else take over. You come back. So if you are having a scenario where you're running it and you've set up the scenario, so this is for other lecturers, teachers, professors, whoever, you're trying to set up a scenario and it's not working, I just want to point out to you that you can tell the process, on this case a thread, to sleep. And when it sleeps, usually it means that it will let go and someone else would have a run and the deadlock can occur. But of course, I do like my examples. It seems everything is working, and as I said, I will share my code so students can test it out. Let me just comment this out in case someone wants to uncomment it and see how it runs. Of course, you can, if you really want to force the deadlock to occur earlier, you can make the sleep value larger. So let me just show you how that happens. So you see, that means because I made the sleep value larger, it means he didn't even sleep for long. So I force almost the first and second thread to lock up. And people sometimes say, oh, but the sleep is artificial. And I say, yes, it is an artificial sleep. But in a real world scenario, you don't control when sleeps happen or when the kernel will be preempted. So you should, especially in testing, test out all the scenarios. People have written their own packages for doing these. A lot of them are available. And this is just a hint to those who do tests. You can put in sleeps. If your code is good, it doesn't matter where it sleeps, it should work. Right? It should work. Now, so it doesn't even make any sense to say I'm not going to debug, but I'll just do the false case where I'll say I want to run this with 10,000 threads, and I am sure this has frozen as well. See, it was running for a while, it just froze. Okay, so let me stop this. The other thing I can do is I can run it in debug mode. It's running and it's frozen. If you have your debugger on, so I have my debugger on, I'm just going to hit pause so you can and while paused, I'm just showing you all the different threads, and some of them are suspended. Of course, things are still moving around. You can try and go through it and figure out who has which thread and so on. But I'm just showing you, there it is. This is NetBeans Deadlock detected. So some of the tools like NetBeans are really have advanced features, and it's saying a deadlock has been detected, and it's just using some of the things we talked about in class. So some of the debuggers can do this. So sorry, that's another output of a run. This is a debugger console. That's the one saying deadlock has been detected. So this is a really cool feature of the debugger. At least this is NetBeans. I don't work for NetBeans or have any formal association with them. I just use the tools. So let me stop everything and let me run this again for those who are wondering how did this happen. So I run it in debug mode. And even though I don't have any breakpoints, I believe it's still able to detect the deadlocks. I'm just running it again. And you see, it keeps running different threads. It's running. And as you watch the list over time, that's the output. I have a lot of threads going on in there. If this takes too long, I'll pause it and I'll let you take a stab at it when there are a few items. Let me see if I can make this run with a few items and see if I can get the deadlock detected, maybe for a smaller number of threads. Okay, and debug mode. If you have a lot of variables being tracked during debugging, it can sometimes slow things down. Okay, so for 100, I didn't run into, and that was what I was just saying. Sometimes you don't run into these deadlocks, and other times you do. Right. So let me look at my. Sorry. I'll save this. You can play with this on your own time. Let me look at the last scenario, and that is some code where there is no deadlock. Right. And the way I did this was to simply say, and you remember what we said during the presentation, especially preventing deadlocks. For the last item, circular wait, we said we can assign strict request order for the resources. And I'm just being creative here, but what I did, if you look at the implementation of Banker, this new version, what it does is to pick up the accounts and find out by the name order. So we'll read the name of the account and find out which one comes before the other in sequential order. So if its accounts are called A, B, C, D, it means A will come before B, B before C, C before D, and so on. And whoever is first is going to lock that one before locking the other one. And that is going to force an ordering on the way locks are done. And that will prevent deadlocks. Right, so I'm going to take a look at this. This is when debugging is true. So I'm just going to start with make it print the messages. So this is for no deadlock, run it. So it ran to the end. Everything looks good. Let's do this again when debugging is false, and this means I'm running with 10,000 bankers. Let's try this to show you that it works. Of course, it's breathing. Yes, it worked, and all the numbers are right. So I want to show you, if you write good code sells itself. Right. So thank you for watching the Java part. Hopefully this takes you through some of the things you can do with code. Now, there were many other things listed during the presentation. I believe you should be able to implement these yourselves. Just listen to the description and then just implement away. Hold and wait, no preemption. All of these you can code. Alright, let's continue.